But the 27th, we don't have school, right?
27th, there's no school. That whole week of the 27th, there's no school.
And is our last day the 11th?
Our last day of class, I believe, is the 11th.
We'll have a test that day, Friday?
Yes.
Okay.
So we'll have lecture today, lecture next week, and then Unit 4 test will be on the 20th. Yeah, then we come back, I think it's the 4th of December. We just have one day of lecture. Then when we come back on the 11th, we'll have a short lecture at the beginning of that class, just because that's a really short test. That test, most people are done within an hour. So we'll have like a half an hour lecture at the beginning of that class on the 11th, and then we'll do our last test. Just because statistics is one of those topics that I could go on all semester about if I needed to, if I wanted to. And believe it or not, in the medical field, statistics are way more important. I mean, it comes into the drug testing side, but it's also on the quality control side of things now too. But anyway, we'll talk about that when we get there. Today we're going to talk about graphing. This is one of those topics that is here for two reasons. One, there are some applications in medicine. If you're tracking stats, a lot of charts have graphs in them. You get into the quality control side of it. You have performance graphs and stuff like that if you're into the management side. The second reason why this is in the course is many of you may know that Wisconsin is moving to requiring 4-year degrees for anybody in the nursing field. So there's a large number of you that will at some point go on to a 4-year degree. And that would require some combination of college algebra and possibly statistics. So the graphing is something you would need for that. So we did a little bit early in the course when we talked about negative numbers, where we worked with number lines. We had the 0 in the middle, positive numbers going off to the right, negative numbers going off to the left. And we had a couple of ways of representing numbers here. When we were doing operations with numbers, we used the vectors. So if I wanted to represent 6, it was a vector that started at 0 and went to 6. But if we're not doing operations with numbers, if we're just expressing the values, probably the simplest way to represent a 6 would have just been put a dot at 6. The vector allows us to do calculations with it, to combine it with other values. But if we're not doing anything with it, if we're just representing that value, a dot is sufficient. We don't need a direction. We just need a location. Well, most of the time when we're working with numbers, it's not just a single value that's important to us. It's a pair of values. For example, instead of just 6, I might want to represent 6 and 2 together. And it is very important that which one comes first is important. For example, this might be saying for a patient that receives 6 doses, they need to have had their blood checked twice. Or something as simple like that, so that you know that there is that relationship. Which number stands for which amount? This is what we call an ordered pair. Pair, obviously, because it's a pair of numbers. Ordered because the order does matter. The number in the first location has a specific meaning. The number in the second location has another specific meaning. To represent them, we could always list them out as an ordered pair, but it's nice to put them in a graphical form like this number line. Now, of course, on a single number line, it would be difficult to do that. I mean, I suppose I could put a dot at 2 and then draw an arrow of some sort indicating that the arrow indicates which one comes first or second, but that would get cluttered very quickly. A man by the name of Descartes came up with the idea that we could represent these two numbers together two-dimensionally, rather than having to put just dots right on a number line. His idea was to use 2 number lines. One that went the regular direction, 0 in the middle, 1, 2, 3, 4, 5 going positive to the right, as always, and 1, 2, 3, 4, negative 5 going negative to the left as always. But then a second number line going vertically, perpendicular. So positive values, 1, 2, 3, 4, 5 going up, and negative values going down. And of course, you can see the 0 point of the two number lines are at the same spot. And that spot has a special name called the origin. It's called the origin because everything originates from there. Everything begins or starts at that point. Both number lines are 0 there, and everything we do to plot points and things like that are going to start from that point. Even when we graph, things are going to start there and move from that point. Each of the number lines is called an axis. The horizontal one is called an independent axis. Quite often referred to as the x-axis, although it can be any variable or any item we want to express there. And the vertical one is called the dependent axis. Again, often called the y-axis, but it doesn't have to be y. It can be any variable that we want to represent there, any quantity we want to represent. Independent for the horizontal axis just means we can pick whatever value we want for that. Dependent for this vertical axis means that once we have the value for this horizontal, for the independent side, that value, the dependent value, is determined. It must be a certain value. So its value depends on the value of the other one, of the other variable. So let me show you how this works now. We're going to plot the 6 and the 2. Well, the 6 was the first number in the ordered pair. That goes on my horizontal axis. The horizontal is always first. It's the independent. The 2 then goes on the vertical axis. It's the dependent variable. Now, obviously, I don't want 2 dots there. So what we do is we look at their projection out into space, their shadows, if you will. And they meet right there. That point that I put in purple, I'll highlight it in red here. If I traced it down to the x-axis, would be 6. Over to the y-axis would be 2. So that point is at the location 6, 2 on my graph. It represents both numbers. So if I put a point right here, what does that point represent?
4, 8.
Yeah, 4 and 8. So the ordered pair 4, 8. Pretend those lines are straight. What's that point represent? -8 and 3. Again, it's just their shadow, where their shadows fall on each axis, or their projections onto the axis. I really wish I was better at drawing sometimes. Like this is one of them. So what's the het point? -4 and -9. Very good. So you guys get the picture as to how to plot these points. And that is the first thing to do. Now be very careful. On a lot of graphs, they're not labeled quite as neatly as mine are here. It's really easy, if you're just looking at the numbers, to be off. I've seen a lot of graphs that get numbered like this. To save space, they might go 1, 2, 3, 4, 5, like that. You have to start at the origin and make sure you know, okay, this is 1 up. Okay, that number goes with that line. So this is the 2, this is the 3, and so on. I mean, otherwise it's really easy. Oh, is this line here, is that the 3 or the 4? Because it's between the two numbers. So make sure you look at that origin and make sure you know what each hash mark actually stands for before you get to it. And it's also not uncommon to have a graph that's labeled like this. What's going on there? Now, each hash mark is 2. This will be 2, 4, 6, 8. Instead of numbering up by 1s, it's numbering up by 2s. So that's also very common. Okay, well, when we go to putting points on the graph, we can have ordered pairs like we just had, where I just gave you the coordinates and you put them on the graph. Or we could have something that defines those. So we might have an equation like this. And what that equation is that's really a family of equations. We have solved equations that might look like this. And by solving that, we just added 2. So 6 equals 3x. And we divided by 3. You get 2 equals x. Well, what this is saying over here is now this value can be anything. And depending on what that value is, x can be any value. Or the other way around. X can be any value, and that'll change what this value is here for y. So rather than having just a single solution like we did here, we have infinitely many solutions. For every value of x, we can get a value of y. Or the other way around. If for any value we want to put in for y, we can get a value of x. So there's no way we can list out all of the possible solutions to this. So there's a couple of things we can do. We can either list a partial set of solutions in a table or ordered pairs or whatever, or we can make a graph. And on the graph we can show some of the solutions, but then show the pattern that allows us to predict or visualize all the other solutions. To make that table, generally what we have to do is, I usually pick values for x. You could pick values for y if you want to, but it's a little bit more difficult because here, let's say I decided to pick -3 as my value for x. Well, now I can very quickly find y by just putting -3 in here and calculating it out. I don't have to solve the equation. I just have a simple order of operations task to do. So let's do that calculation. If x is -3, y is then going to be 3 times -3 and minus 2. Well, what's 3 times -3? -9. Then minus 2 is -11. Very good. So what this is telling us is when x is -3, y is -11. So we have -3, -11. So on my graph, -3, -11. Somewhere in there, there's a point. Now, if we're looking at if we have a grid in front of us that might be off our grid or whatever, that doesn't matter. We'll find other points that will be on the grid. So let's try another value. Maybe I'll try -1 for x. So if x is -1, y is 3 times x minus 2, so 3 times -1 minus 2. 3 times -1 is -3, very good. -3 minus 2 is -5, great. So now we have this ordered pair. What number comes first? X, that'd be -1, comma, -5. So we have -1, -5 is somewhere in there. So we might pick 0. I always like using 0 for x because that's usually pretty easy to do. 3 times 0 minus 2. Well, 3 times 0 is 0. Minus 2, -2. Giving us the ordered pair, 0 and -2. Perfect. So that puts us at 0. -2 is right there. Right on our axis. Well, we might need some more points. Let's do 1 for x. So if x is 1, y is 3 times 1 minus 2. 3 times 1. 3 minus 2 is 1. So 1, 1 is a point. Now at this point we probably have enough points. We realize these are all in a straight line. So we need to draw a line through it. Pretend the line I drew out there is straight. What does that line represent? Well, that line represents every possible solution to this equation. You know, we just had when x is 1, y is 1. If I came over here where x is 2, y would be 4. But not only that, but we could have, if x was 1.3, y would be 1.9. Every possible solution, every possible value of x. If I pick a point, that's the value of x. That's my value of y. That gives me every possible point. There's an infinite number of them. I mean, no matter how close together I get, you can always find a point in between them. So that's all the solutions that would make the equation y equals 3x minus 2 true. Now, not all of our equations are going to make straight lines on the graph. We can run into an equation like this. Now I'm going to pick values for x, and I'm going to try them in here, put them into the equation, and see what y has to be. So I might have, well, let's try -2 for x. Well, then y has to be -2 squared plus 2 times -2 minus 15. Now I'm going to pause right here. Anybody have any questions as to where this came from? All I'm doing is taking this equation here, y equals that. So I'm putting in this value that I chose for x, where the x is. So -2 squared, 2 times -2, and then minus the 15. So a couple things to do here. What's -2 squared? Positive part. Careful on your calculators. If you punch that in incorrectly, -2 squared, it'll try to tell you -4. Anything squared is always positive. On this next test in 2 weeks, I will catch at least 4 or 5 people in the group that'll put that in their calculator and get negative, and their graph's going to look strange. Make sure you put parentheses around your negative when you square it. Yes. 2 times -2 is, that one is a -4. Positive times a negative. Then minus 15. Well, 4 plus -4 is 0. Minus 15 is -15. That point is probably not horribly useful to us right now. Because -2 I guess I do have room on this graph, but on most of the graphs we use, we wouldn't have room to put a -15 down there for y. So this is the ordered pair, -2, -15. Well, let's see what happens when I put in a -1 for x. Oops, -1, -2. So it's -1 squared plus 2 times -1 minus 15. So -1 squared is +1 plus 2 times -1 is a -2 minus 15. Well, 1 plus -2 is -1 minus 15. That's -16. That's even worse. So you got -1, -16 is our ordered pair. That's going to be down here. Let's try 0. If x is 0, y is 0 squared plus 2 times 0 minus 15. What's that going to be? 0. What's that going to be? 0. So 0 plus 0 minus 15 is just negative 15. So 0 and negative 15, which is right there. So let's keep going. First thing we know right now is that this is definitely not a straight line. Looks like kind of a V pattern right now. Let's try 1 for x. So then y is 1 squared plus 2 times 1 minus 15. 1 squared is 1. 2 times 1 is 2, and then minus 15. 1 plus 2 is 3. Minus 15 is negative 12. So we're now at 1, negative 12. So positive 1, negative 12 is right there. Now looking at this, this is where you might have some given values of x that you try to get some points. Once we start getting some points on the graph, it helps us decide where do we need more points at. Well, right now we can see it looks like the value is going to get larger as we go in each direction. So let's move out away from this point. This is at x equals negative 1 here. Let's move out away from that a little bit. So let's try maybe x equals negative 4. See what happens if we go there. So x equals negative 4. So we're at negative 4 squared plus 2 times negative 4, and then minus 15. In your notes, find what this comes out to be here for y. Pretty common. It happens. What'd you come up with? Negative 7. Very good. So we got the coordinate negative 4, negative 7. So negative 4, 3, 4, negative 7. Right about there. Let's try positive 3. So let's do 3 squared plus 2 times 3 minus 15. 3 squared is 9. 2 times 3 is 6. Minus 15. Well, 9 plus 6 is 15. Minus 15 is 0. So we have 3, 0 is that point. So 1, 2, 3, 0 right there. So we have these points right now. And if we weren't sure of ourselves, we could find other points. If you just pick different numbers, you'd find other points that we could plot on the graph. What we get is we get this kind of a cross between a U and a V. It's not a V because it doesn't come to a sharp point. It's rounded and it curves on the sides. Called a parabola. You don't need to know that term. We're not going to get into parabolic equations or quadratic equations. And we're going to do a lot of linear stuff. But you do need to be able to put numbers into a table like this and find what, plot them on the graph and see what they're going to look like. Okay, so what I want to do right now is I've got this worksheet that I'm going to put up. And I'm going to do this. I'm going to put it up on the board. And I want you to either work alone or with somebody next to you if you want to. And I want you to try. I'm going to pull that up just a little bit further so it's a little bigger for you. Plug the numbers. I gave you the numbers here to try for x. I didn't give you any room here to figure it out, but you'll do that in your notes. Plug these numbers in for x. Figure out what values would go for y. Plot them on a graph and see what you get for a graph. So I want you to try these two quick. I'll give you 5 minutes or so, and then we'll talk about them and see if you guys come up with what I do. Then we'll skip to some other ones.